In this presentation, we will discuss some of the anthropogenic sources of bromide. This work was prepared in collaboration with Butts County by researchers at the University of Georgia, with financial support from Butts County and a regional water plan seed grant from the Georgia EPD. Starting in the 18th and 19th centuries, bromide was used at a small scale for photograph development and as a sedative in human medicine. However, the first substantial anthropogenic release of bromide into the environment occurred during the proliferation of the global automobile industry from the 1920s to the 1990s. During that period, brominated compounds were added to leaded gasoline to act as a scavenger and prevent lead deposition from damaging car engines. Engine combustion activities emitted these brominated compounds as methyl bromide. Another historical anthropogenic source of bromide was the widespread agricultural use of methyl bromide as a fumigant and soil sterilizer from about the 1960s to the 1980s. When it was discovered that methyl bromide contributed to ozone layer depletion, its use was drastically reduced by the 2000s under the 1987 Montreal Protocol. Although most of the methyl bromide released into the environment volatilizes into the atmosphere, between about 10 to 30% remains in the soil and is broken down into bromide. Finally, bromide has been released as a waste product of potassium or potash mining activities and found to elevate surface water bromide concentrations in several European countries, especially in the Rhine River watershed. Salt mining is still a major industry in various parts of the world and continues to create water quality issues when brines pollute source water. Current anthropogenic sources of bromide include energy extraction and utilization, coal-fired power plants, water treatment, flame retardants, pre-planting and post-harvest biocides, agricultural herbicides, municipal waste incinerators, landfill leachate, road deicers, and pharmaceuticals. Anthropogenic bromide contaminated surface waters from energy extraction and utilization activities in the U.S. is well documented. Wastewater from conventional oil and gas extraction is high in bromide, and if it's not stored in an injection well, it's sent to a wastewater treatment plant. Since wastewater treatment plant facilities are not required to meet discharge limits on dissolved solids, discharges from these facilities result in bromide loading in surface waters. Hydraulic fracturing, or fracking, is an unconventional gas extraction process in which shale rock is exploited via drilling and high-pressure injection of water, sand, and other chemicals are used to release gas. Wastewater from the fracking process is enriched by the minerals that compose shale, including bromide. The wastewater is subsequently discharged into surface waters, elevating the bromide concentrations and the potential for creation of disinfection byproducts following chemical disinfection. Coal contains bromide at trace levels, but these concentrations can vary depending on the source mine surrounding geology. Coal combustion shifts bromide to bromine and flue gas. Bottom ash, fly ash, and gypsum do not typically contain significant bromide levels following coal combustion. However, in plants that use a wet flue gas desulfurization system, along with the intended conversion of gaseous sulfur dioxide to soluble sulfuric acid, gaseous chlorine and bromine are converted to soluble chlorine and bromide in FGD wastewater. Power plant treatment systems do not remove halogens from FGD wastewater before releasing it to surface waters, so this can be a significant source of anthropogenic bromide pollution in source waters. Further, since the EPA's air toxic standard was enacted, which requires mercury emissions to be reduced by 90%, many coal-fired power plants have turned to bromide addition technologies for enhanced mercury removal. As summarized in Van Briesen, 2014, in FGD systems where added bromine for mercury control, bromine gas oxidizes elemental mercury gas to ionic mercury, which leads to the formation of mercury halogen salts. These salts are soluble and can be captured in wastewater, which is then treated by a wastewater plant to remove mercury prior to discharge. However, there is no treatment to remove high levels of bromine in the wastewater that result from the bromine addition. Thus, wastewater from wet FGD systems using bromide addition for mercury control is still an important anthropogenic source of bromide. Bromine chlorine biocides are used as an anti-fouling agent in power plant cooling towers to prevent microbial growth. Wastewater produced by these cooling towers contains low bromide levels that may contribute to surface water bromide elevation. Paper and pulp mills also use bromide to prevent microbial contamination with bromide levels of up to 100 milligrams per kilogram measured in wastewater sludge. Other applications of bromine chlorine biocides include decontamination of water used for agriculture, chemical production, brewery pasteurization, and swimming pools. The widespread and regular use of bromine chlorine biocides is of note because the final product yield is typically bromide. Brominated flame retardants are cheaper and more effective than those containing chlorine, so they are widely used throughout the world in electrical equipment, textiles, building and construction, and vehicles. Although BRFs can produce significant disinfection byproducts when exposed to an oxidizing agent, the primary concern associated with BRFs is the release of bromide-rich wastewater from production facilities into surface water. Although the use of methyl bromide has drastically declined since it was discovered to deplete the ozone layer, small quantities are still allowed for pre-planting soil fumigation and post-harvest quarantine of crops and logs. As previously mentioned, most of the methyl bromide volatilizes into the atmosphere, while about 10 and 30% remain in the soil and is broken down into bromide, which can enter surface water. Although the use of popular bromine-containing agricultural products, for example, fumigants and pesticides, has been drastically reduced or eliminated due to environmental health concerns, the use of bromacil as an herbicide continues today. Bromacil is regularly applied to citrus and pineapple crop fields for weed control. It is both persistent and mobile in the environment, meaning that it can readily enter surface and groundwater surrounding agricultural areas. A recent study demonstrated that brominated disinfection byproducts were formed following chlorination of water containing bromacil. As previously described, there are a variety of bromine-containing products, especially brominated flame retardants, that ultimately end up as solid fuel in municipal waste. Municipal waste incinerators have been shown to significantly contribute to elevated bromide in surface waters. Leachate from landfills, or municipal solid waste storage sites, which have high levels of bromide, have also been found to contaminate nearby surface and groundwaters. Brine or road salt, as road deicers, may represent non-point runoff bromide sources for surface waters in some regions. However, recent work in North Carolina did not find that road deicers significantly contribute to surface water bromide levels. The number of pharmaceutical products that contain bromine is growing and include natural and synthetic products. However, the current scale of production and use for these compounds, it is unlikely that pharmaceuticals containing bromine are a significant driver of elevated bromine in surface waters. In addition to water scarcity in times of extended drought, low surface water discharge will reduce the dilution capacity of source water. Diminished dilution capacity will lead to higher source water bromide levels and increased concentrations of disinfected byproducts in finished drinking water. Alternatively, severe storms and flooding events can lead to increased contaminants in source water via surface water runoff and sediment resuspension. Increasing water temperatures will increase kinetics of reactions between disinfection byproduct precursors and chemical disinfectants, leading to greater concentrations of DPBs in finished drinking water. Rising sea levels will lead to saltwater intrusion into coastal source waters. Saltwater intrusion will impair coastal aquifers and estuaries via increased water temperature and bromide content, and this would subsequently present greater potential risks to consumers.